In the name of Almighty God, I'm Master Sankoshi, and today I want to talk about introduction about plasma ICP, CCP, argon, chlorine. This tutorial uses the inductively coupled plasma with a radio frequency bias interface to model an argon chlorine inductively coupled plasma reactor with radio frequency bias, also known as ICP and CCP. This is ICP because inductively coupled plasma and also CCP. The inductively coupled plasma with radio frequency bias interface is used to study discharge that are sustained by induction currents and have an additional time periodic electric excitation. This interface adds the plasma time periodic and magnetic fields interfaces. The magnetic field is solved in the frequency domain and the plasma solves for a periodic solution. The multiphysics coupling coupled the time average plasma conductivity to the magnetic field's interface and coupled the resulting electron heating due to induction currents back to the plasma time periodic interfaces. It is also shown how to prepare a model with a mixture of different elements, in this case argon and chlorine, in which one of the species can dissociate by electron impact. Chlorine dissociates into chlorine 1, and where negative ions exist, the dissociative electron attachment of chlorine creates chlorine negative. A simplified plasma chemistry is used to discuss the main aspects of such discharge. It is important to keep in mind that a benchmark is not attempt, and the idea is to provide a base case that can be used to develop more complex chemistries. In fact, it might be necessary to modify the data used and to add more reactions to achieve experimental verification. In this model, the many features used to set up the plasma chemistry are created automatically from a text file by using the plasma chemistry add-in. Now I want to go through the model definitions. The plasma model is solved self-consistently with the magnetic fields, laminar flow, and heat transfer in fluid interfaces. The plasma transport reactions equations coupled with Poisson's equation are solved in the time periodic fashion, allowing for the description of the different quantities along the period. In this way, electrons exhibit periodic modulation caused by the radio frequency bias. The magnetic field interface is solved in the frequency domain. The Joule-Jing term obtained from the magnetic field interface is thus an average quantity and is given to the electron mean energy equation as a constant value along the period. The plasma conductivity used in the magnetic field equations is computed from the periodic average quantities obtained using the plasma time periodic interface. The laminar flow and heat transfer in fluids interfaces are solved in a stationary form, and consequently all parallel evolution is neglected. The fluid and thermodynamic properties computed in the plasma model and passed to the laminar flow and heat transfer in fluids interfaces or period average quantities. In particular, this model assumes that heavy species only exist in the base geometry. This means that ions and neutrals don't have a period modulation or modulation and only experience a time average electric fields. Now I want to talk about electric excitation. There are two independent forms of electric excitation present in this model: the inductively coupled power controlled by the coil, the capacitively coupled power controlled by the radio frequency bias. For the non-magnetized, non-polarized plasma, the induction currents are computed in the frequency domain using the following equations, such as j omega sigma minus omega to the power of 2 epsilon 0 multiplied by r b plus delta multiplied by micro 0 to the power of minus 1 multiplied by r is equal to j to the power of e. The electromagnetic excitation C is a plasma defined by the plasma conductivity in the cold plasma approximation that is set in the plasma conductivity coupling. Multiphysics features such as sigma is equal to NaQ to the power of 2 divided by MaE multiplied by VaE plus J omega. Here Na is the period average electron density, Q is the electron charge, Ma is the electron mass, Va is the period average collision frequency, and omega is the angular frequency. The Joule heating term, which represents the heating of the electrons, is set in the electron heat source multiphysics feature. The bias electrode is driven by sinusoidal excitation and constant voltage amplitude. Vs is equal to V radio frequency cosine uh, 2p FAPT plus alpha plus via direct current and B. The DC bias voltage via DC B is computed so that the net current over a period is zero. Plasma boundary conditions: electrons are lost to the wall due to the random motion between a few mean free passes of the wall and gain due to the secondary emission effects, resulting in the following boundary condition for the electron flux. And tau is equal to 1 divided by 2 VATH NAE. And the electron energy flux is equal to N multiplied by tau epsilon is equal to 5 divided by 6 multiplied by VATH NA epsilon. For the heavy species, ions are lost to the wall due to the surface reactions and the fact that the electric field is directed toward the wall. And Jk is equal to MW RK plus MW CK Z micro K En ZK micro K En is greater than 0. The walls of the reactor are grounded with the exception of the bias electron. Now I want to go through the plasma chemistry. Negative ions are created in the certain molecular gases discharged like chlorine, oxygen, hydrogen, fluorocarbons, and so on. And these charges tend to have complex plasma chemistries with many ions, dissociated products, and excited states. Here, simple plasma chemistry is used and no benchmark is attempted. In fact, it might be necessary to modify the data used and add more reactions to achieve experimental verification. Nevertheless, this plasma chemistry allows to show the main aspects of an electronegative discharge. The plasma chemistry should be adapted and improved for specific applications as needed. One aspect that emerges from analyzing model results of the present model is that the dissociation degree is high. Knowing this is that it might be needed to add more reactions involving chlorine. The plasma chemistry used here includes electron impact reactions from reference 1 and reference 2, and some reactions are estimated from similar reactions based on data from reference 3. A good discussion of plasma chemistry for electronegative gases can be found in reference 4, in particular in the section A data set for oxygen, page 270 on reference 4. A set of reactions for oxygen discharge is discussed. Argon is one of the simplest mechanisms to implement at low pressures. The electronically excited states can be lumped into a single species, which results in a chemical mechanism consisting of only three species and seven reactions presented in Table 1. Electron impact cross sections are obtained from reference 1. Chlorine has a much richer reaction set that includes vibrational and rotational excitations, excitation of several electronic excited states, electron impact dissociation, dissociative attachment, and many others. Electron impact reactions with chlorine 2 are from reference to except for E plus chlorine, which is included chlorine plus 2 electron and electron plus chlorine as a negative, which includes chlorine plus two different electrons, which are estimated from several reactions from reference 3. Electron impact reactions are neglected except for electron plus chlorine, which is included chlorine plus 2 electron for simplicity, rotational, vibrational, and electronic excited states are not treated explicitly, but energy losses are considered. The chlorine electron impact reactions used in this model are presented in table 2. As you see, we have a dissociative attachment, elastic Vibrational excitation, I want to read the formula. A plus 2 chlorine, which is given chlorine plus chlorine, negative is a dissociative attachment. Electron plus chlorine 2, which is given electron plus chlorine 2 is elastic. Electron plus chlorine 2, which is given electron plus chlorine 2 is a vibrational excitation. Electron plus chlorine 2, which is given electron plus chlorine 2 is a vibrational excitation. Electron plus chlorine 2, which is given electron plus chlorine dissociative excitation. Electron plus chlorine 2, which is given electron plus chlorine 2 is excitation, and so on. For example, we have an electron plus chlorine 2, which is given 2 electron plus chlorine 2 positive is the ionization. Table 3 presents the heaviest species reactions involving ions. All these reaction rates are estimated from similar reactions from reference 3. In addition to volumetric reactions, table 4 lists the surface reaction implemented, such as this. Boundary conditions for heavier species are introduced in a model by using surface reactions. If no surface reactions that lead to the loss of a given species at a surface are introduced in the model, that species will not have losses by transport. This can lead to the unbounded growth of a given species, and steady-state solution might not be possible. Atomic recombination reaction 3 in table 4 at the surface is an important aspect of plasma discharge with molecular species since it influences the dissociation degree in the discharge. The sticking coefficient for atomic recombination is a function of the surface type and temperature. Electromagnetic plasmas. Electromagnetic and electronegative plasma are plasma that contains negative ions. Negative ions are mainly created by electron dissociative attachment. This reaction tends to be very far effective at low electron energies and can be reduce the electrons in a discharge to the point that an ion discharge is obtained. The transport and volume creation destruction mechanism tend to be more complex and electropositive plasmas in many respects. Here only a few are mentioned with emphasis on the numerical difficulties that they introduce. More information can be found in reference 4, section 10.3 and references therein. In electronegative discharge, negative ions are well confined by the bipolar electric field and losses by transport are very small. This means that to achieve a steady-state volume, losses need to be included for negative ions. The mechanisms by which negative ions are lost depend on the gas mixture and pressure, and they are mutual combination with positive ions. For example, chlorine negative and chlorine positive, which is given 2 carbon or chlorine negative plus argon positive, which is given chlorine and argon detachment in collisions with excited or natural atoms or molecules. For example, chlorine negative and chlorine, which is given 2 chlorine plus electron, or chlorine negative plus 2 chlorine, which is given chlorine plus 2 chlorine plus electron. And electron impact detachment, for example, electron plus negative chlorine, which is given chlorine plus 2 electron. In electronegative discharge, it is often possible to identify two spatial regions using the electronegativity ratio of the negative ion density to the electron density. One in the core of the discharge, the electronegative core with high electronegativity, which their dominant charge species are positive and negative ions, and the other close to the boundaries, electropositive edges, where the dominant charge species are electron and positive ions. In the transition between these two regions, the negative ion density drops abruptly, causing a choke-like phenomenon. This transition needs to be well resolved spatially. If not, oscillations can be seen in the negative ion density and the model might not converge. Some strategies to deal with this are increase the negative ion diffusion coefficient or decreasing its mobility. When using the option compute mobility and diffusivity, the mobility is computed using Einstein relation, which by default uses the gas temperature, but specifying a higher ion temperature results in a smaller mobility, enable isotropic diffusion for ions in the inconsistent stabilization section. The stabilization sections are visible when the stabilization is selected in show more options. These options adds artificial diffusion to all ions and helps smoothing the sharp transition of the negative ion density between the electropositive edge and the electronegative core, and so also increase the density of the negative ions in the electropositive edge, effectively increasing its losses by transport. This option should be used very carefully since completely wrong results can be obtained if too much diffusion is used. The tuning parameter for ions should not be larger than zero point 0.1. A useful strategy is to start with a large tuning parameter for ions, for example zero point 0.5, and ramp it down using the auxiliary sweep. Now I want to go through the inflow and outflow. The inflow boundary condition fixes the mass fraction or mole fraction of a specified species. It is used in this model to set the mole fraction of the inlet mixture at the boundary. The fluid velocity is computed and set at the same boundary by the inlet feature of the laminar flow interface. At the inflow boundary condition, the model fraction of chlorine is set to a small number so that the mole fraction of argon chlorine is always respected at the boundary. When dissociation is high, the mole fraction of argon can be different than specified because the mass fraction of argon is obtained from a mass constraint, and in fact no explicit constraint is applied at the boundary. The outflow boundary condition removes transport by diffusion at the boundary, but it is still keeps transport by convection and migration in the electric field. The outflow boundary condition only sets boundary conditions for heavy species to model a net outflow out of the system. The outlet boundary condition of the laminar flow interface should be used when solving for the plasmas with chemistries that contain more than one element, for example argon and chlorine 2 with a stationary solver. The mass fraction of each element is not conserved if no constraint is used. This problem is similar in nature to the one found when solving for numerous Stokes equations in a steady state without fixing the pressure somewhere. As a strategy to overcome these problems, one can fix the mole fraction of a given species using the inflow boundary condition even if no fluid flow exists in the system. In the present model, it is assumed that the charged species electrons and ions are lost by transport at the inflow and outflow boundaries. This is the model by applying the surface reactions for ions and the wall feature for electrons. This could represent a metal grid boundary that allows the neutral gas to flow through it, while the plasma sees a metal boundary. It is also assumed that the argons and chlorine can react at the inflow and outflow boundaries. To adjust the probability of reaction to acquire at the surface, the forward sticking coefficient in the surface reaction feature can be adjusted. As an example, to model a 50% probability of argons to react at the outflow grid, the forward sticking coefficient should be set to the zero point 0.5. Solution strategy. The recommended solution strategy to model an inductively coupled plasma with radio frequency bias is as follows. First, solve the problem with inductively coupled plasma only. To speed up this study, set the number of electrons in the extra dimension settings to 1. Since there is no radio frequency bias applied, yet it is not necessary to have resolution along the period. Afterward, add a second study that uses the solution of the previous study as initial conditions. Increase the number of elements to value in the range 30 to 50 and use the auxiliary sweep to increase the amplitude of the applied voltage. For pure CCP problems, it is advised to set the terminal type to power in the metal contact feature because it makes the numerical problem much easier. For ICP-CCP models, it is advised to set terminal type to voltage. At the bias electrode, the electrons can exhibit a strong period modulation and can attain as high energies as in a pure CCP reactor. For these reasons, the space and period resolutions need to be as high as in a pure CCP reactor model. Now I want to go through the result and discussion. Figure 1 to figure 3 show the period average spatial distribution of the electron density, electron temperature, and electron potential for 250 watt of coil power, and via voltage for radio frequency is equal to 100 volt. The electron density is relatively low, almost 10 to the power of 16 1 per cubic meter, and has a flat profile in the core of the discharge, where the dominant charge species are the ions of chlorine, natron, with the number densities of the order of 10 to the power of 17, 1 per cubic meter. This makes the discharge have high electronegativity in most of the reactor. At the edge, the negative ion density decreases fast and the plasma becomes electropositive. The dominant power curve to the system is inductive and is responsible for maintaining a high plasma density. The radio frequency bias influences the plasma density significantly, but the electron temperature changes from having a maximum just below the coil for voltage radio frequency is equal to 0 volt to a maximum at the bias electrode for higher voltage. From the period average potential, it is possible to see that a DC or direct current bias of a blue about minus 75 volt is developed at the bias electrode. This is also possible to see from the period evolution of the average voltage figure 4. This figure also shows the current at the electrode, which strongly deviates from a sinusoidal and has a strong contribution from the electron current when the sheet collapses. Figure 5 and Figure 6 show the magnitude of the fluid velocity and the gas temperature respectively. The fluid pattern, as expected, has its maximum at the inlet, and the trajectory strongly connects to the outlet with the region at the symmetry axis having low fluid velocities. The background gas temperature attains 1000 Kelvin with elastic collisions of the electron, with the background gas being the main heating mechanism. You see, figure 1 shows period average electron density for 250 watt of coil power, and voltage for radio frequency is equal to 100 volt. And the next one is surface electron temperature period average, as based on the volt. Figure 2 shows period average electron temperature for 250 watt of coil power, and voltage radio frequency is 100 volt. And figure 3 illustrates the period average electric potential for 250 watt of coil power, and voltage rated frequency is 100 volt. And you see another plot. Figure 4 illustrates current and voltage at the bias electrode for 250 watt of coil power, and voltage for radio frequency is 100 volt. Another is surface velocity magnitude based on the is meter per second. Figure 5 shows magnitude of the fluid velocity for 250 watts of coil power, and voltage radio frequency is equal to 100 volt. And another is a figure 6 illustrates gas temperature for 250 watt of coil power, and voltage radio frequency is equal to 100 volt. The reference says that I have read this literature was written by Phillips database and also Siglo database, a Friedman plasma chemistry, Cambridge University Press, and other one is Lieberman and Lichtenberg, a principal of plasma discharge and materials processing by John Wiley and Sons in 2005. Thank you so much for watching my tutorial video on today. And today is the second day of the May 2026. Time is 8:03 o'clock in the morning, and also you can download the proper and appropriate Compton multiphysics simulation files from my github.com/master script.